So today I'm reading a paper called Image Segmentation Using Deep Learning, a survey. Abstract is image segmentation is a key topic in image processing and computer vision with applications such as scene understanding, medical image analysis, robotic perception, video surveillance, augmented reality, and image compression, among many others. Various algorithms for image segmentation have been developed in the literature. Recently, due to the success of the deep learning models in a wide range of vision applications, there has been a substantial amount of work aimed at developing image segmentation approaches using deep learning models. In this survey, we provide a comprehensive review of the literature at the time of this writing. Covering a broad spectrum of pioneering works for semantic and instance-level segmentation, including fully convolutional pixel labeling networks, encoder-decoder architecture, multiscale and pyramid-based approaches, recurrent networks, visual attention models, and generative models in adversarial settings. We investigate the similarity, strengths, and challenges of these deep learning models, examine the most widely used datasets, report performance, and discuss promising future research in directions in this area. Introduction. Image segmentation is an essential component in many visual understanding systems. It involves partitioning images or frames into multiple segments or objects. Segmentation plays a central role in a broad range of applications, including medical image analysis, tumor boundary extraction and measurement of tissue volumes, autonomous vehicles, navigable surface and pedestrian detection, video surveillance, and augmented reality, to count a few. Numerous image segmentation algorithms have been developed in the literature, from the earliest methods such as thresholding, histogram-based bundling, region growing, k-means clustering, watersheds, to more advanced algorithms such as active contours, graph cuts, conditional Markov random fields, and sparsity-based methods. Over the past few years, however, deep learning networks have yielded a new generation of image segmentation models with remarkable performance improvements, often achieving the highest accuracy rates on popular benchmark, resulting in what many regard as paradigm shift in the field. For example, Figure 1 represents a sample image segmentation outputs of a prominent deep learning model. Image segmentation can be formulated as a classification problem of pixels with semantic labels, semantic segmentation, or partitioning of individual objects inside segmentation. Semantic segmentation performs pixel-level labeling with a set of object categories, for example, a human, car, sky, for all image pixels. Thus, it is generally a harder undertaking than image classification, which predicts single label for entire image. Image instance segmentation extends semantic segmentation scope further by describing and delineating each object of interest in the image. For example, partitioning of individual persons. Our survey covers the most recent literature in image segmentation and discusses more than 100 deep learning-based segmentation models proposed until 2019. We group learning-based works into following categories based on their main technical contributions: fully convolutional neural networks, convolutional models with graphical models, encoder-decoder based models, multiscale and pyramid-based networks-based models, RCNN based models for instant segmentation, dilated convolutional models, and deep lab family, recurrent neural based models, attention based models, generative models, and adversarial training. Convolutional models with contour models, with active contour models, and other. Key contributions of this survey paper can be summarized as follows. This survey covers contemporary literature with respect to segmentation problem and overviews more than 100 segmentation algorithms proposed till 2019, grouped into 10 categories. We provide a comprehensive review and insightful analysis of different aspects of segmentation algorithms using deep learning, including the training data, choice of network architectures, loss functions, training strategies, and their key contributions. We provide an overview of around 20 proper image segmentation datasets groups into 2D, 2.5D, RGBD, and 3D images. We provide a comparative summary of properties and performance of reviewed methods for segmentation purposes on popular benchmark. We provide several challenges and potential future directions for deep learning-based segmentation. Okay. Overview of deep neural networks. In this section, we provide overview convolutional neural networks. CNNs consist of three types of layer: convolutional layers, where the kernel filter of weights is convolved in order to extract feature; non-linear layers, which apply an activation function on the feature maps; pooling layers. The units and layers are locally connected, that is, in each unit receives weighted inputs from a small neighborhood by stacking form a multi-resolution pyramids. Higher layers learn features from increasingly wider receptive fields. Recurrent neural network, widely used to process sequential data. RNNs are typically problematic with long sequences, as they cannot capture long-term dependencies in many real-world applications. Type of RNNs called long-term, short-term memory is designed to avoid these issues. LSTM architecture figure 4 includes 3 gates: input gate, output gate, and forget gate. Encoder-decoder autoencoder models. Figure 5 illustrates the block. Let me start from the beginning. The encoder-decoder models are a family of models which run to map data points from input domain to output domain via two-stage network. The encoder represents the encoder represented by a counting function compresses the input in the latent state representation. The decoder aims to predict the output from latent state representation. Latent representation here essentially refers to feature vector representation, which is able to capture the underlying semantic information. These models are popular in image-to-image translation, as well as for sequence models in LNP, trained by minimizing construction loss. Output can be enhanced version of the image. Autoencoders are a special case of encoder-decoder, which input and output are the same. Several variations of autoencoders have been proposed. Variational. Another popular variant is the variational autoencoder, which imposes a prior distribution on latent space. VAEs are able to generate realistic samples from given data distribution. Generative adversarial networks. Generative sample fakes can also minimax game between G and D. Since invention of GANs, researchers have endeavored to improve, modify GANs in several ways. For example, Redford proposed convolutional GAN model, which works better than fully connected, and so on. Transfer learning. In some cases, DL models can be trained from scratch. You can use transfer learning. Pre-trained should be able to capture semantic information of the image required for segmentation and therefore enabling them to train model with less labeled samples. DL-based image segmentation models. This section provides a detailed review of more than 100 deep learning-based segmentation methods proposed until 2019, grouped into 10 categories. It is worth mentioning that these are some pieces that are common among many of these works, such as having encoder and decoder parts, skip connections, multiscale analysis, and the more recently the use of dilated convolution. Fully convolutional networks. Deep learning works for segmentation using the convolutional network includes only convolutional layers, the skip connections in which feature maps from the final layer of the model are upsampled and fused with the feature maps of earlier layers. The model combines semantic information and appearance information in order to produce accurate and detailed segmentations. This work is considered a milestone in image segmentation, demonstrating that deep networks can be trained for semantic segmentation in end-to-end manner on variable-sized images. However, despite its popularity and effectiveness, the conventional FCN model has some limitation. It is not fast enough for real-time inference. It does not take into account the global context information in an efficient way. It is not easily transferable to 3D images. Convolutional models with graphical models. As discussed, FCN ignores potentially useful scene-level semantic context. To integrate more context, several approaches incorporate probabilistic graphical models such as conditional random fields and Markov random fields into DL architecture. Chen proposed a semantic segmentation algorithm based on a combination of CNN and fully connected CRFs. They show that responses from final layer of deep CNN are not sufficiently localized for accurate object segmentation due to the invariance properties that make CNN good for high-level tasks such as classifications. To overcome the poor localization property of deep CNNs, they combined the responses at the final CNN layer with a fully connected CRF. They showed that the model is able to localize segment boundaries and at higher accuracy rate than it was possible with previous methods. Okay, figure 10. A CNN per CRF model. The coarse score map of CNN is upsampled via interpolation and fed to fully connected CRF to refine the segmentation result. So we have input, final output. So first we go through the convolutional neural network, get the coarse score map, do linear interpolation, then use fully connected CRF and get the final output. Encoder-decoder based model. Another popular family of deep models for image segmentation is based on convolutional encoder-decoder architecture. Most DL-based segmentation works use some kind of encoder-decoder models. We group these works into two categories: encoder-decoder models for general segmentation and image segmentation. Model VG 16-layer network in order promising signal as segmentation net. Their model consists of two parts: encoder using convolutional layers adapted for VG16 layer network, and deconvolutional network that takes feature vectors input and generates map of pixel-wise class probabilities. The deconvolutional network is composed of deconvolution and unpooling layers which identify pixel-wise class labels and predict segmentation masks. In another promising work known as SegNet, Badrian proposed a convolution encoder architecture for image segmentation. Similar to the convolutional network, the core trainable segmentation engine SegNet consists of encoder network, which is topologically identical to 13 convolutional layers. Figure 15, the PSPN architecture. A CNN produces feature map and a pyramid pooling module aggregates the different subregions representations. Upsampling and concatenations are used to form the final feature representation from which the final pixel-wise prediction is obtained through convolution. Multiscale and pyramid network-based models. Multiscale analysis, rather old idea in image processing, has been deployed in various neural network architectures. One of the most prominent models of this sort is the feature pyramid network (FPN) proposed by Lin et al., which was developed mainly for object detection but was then also applied to segmentation. Alright, let's continue. RCNN. Getting a little bit low on the time. Dilated convolutional. Okay, let's have a look at this timeline. 2040 CNN plus CRF, FCN, VG16, 2015 deep mask, 2016 instance aware segmentation, 2017 mask RCNN, 2018 mask lab, 2019 tensor mask. Section 5 Performance Review. We provide a summary of some of the popular metrics used in evaluating the performance of segmentation models, and then we provide quantitative performance of promising DL-based segmentation models on popular datasets. Metrics for segmentation model: pixel accuracy, mean pixel accuracy, intersection over union, recurrent index, precision recall, dice coefficient. Challenges and opportunities. There is no doubt that image segmentation has benefited greatly from deep learning, but several challenges lie ahead. We will next introduce some of the promising research directions that we believe will help in further advancing image segmentation algorithms. More challenging datasets. Several large-scale image datasets have been created for semantic segmentation and text segmentation. However, there remains need for more challenging datasets as well as datasets for different kinds of images. Its rising popularity of 3D image segmentation Interpretable deep models, weakly self-supervised, unsupervised, real-time models for various applications, memory-efficient model, 3D point cloud segmentation. Numerous works have worked on 2D image segmentations, but much fewer have addressed 3D point cloud segmentation. However, there has been an increasing interest in point cloud segmentation, which has wide range of applications: 3D modeling, self-driving cars, robotics, building modeling, etc. Dealing with 3D unordered and unstructured data, such as point clouds, poses several challenges. Graph-based deep models can be a potential area of exploration for point cloud segmentation. Conclusions. We have surveyed more than 100 recent image segmentation algorithms based on the deep learning models which have achieved impressive performance in various image segmentation tasks. Benchmarks grouped into 10 categories such as CNN, FCN, RNN, RCNN, and the latest CNN, attention-based model, generative, and adversarial, among others. We summarize quantitative performance analysis of these models on popular benchmarks such as Pascal, VOC, MC, COCO, Cityscapes, and ADE20K datasets. Finally, we discussed some of the open challenges and potential research directions for image segmentation that could be pursued in coming years. And that's all, folks. Thank you for listening. And